I'm back with another driver test. Today it's a variation of the Vifa XT25. The reason why I bought these originally was for a project I did. There was an event in a competition in New York that a friend of mine was going to, and he built the boxes and I did the design and we won. You had to use a specific woofer. It was a Peerless 830656. We chose this tweeter and it got the best overall sound. So I already know this is a proven winner. It's a great tweeter and I'm going to measure it today to remind myself what it's capable of. And I'm thinking about using it in a desktop design, which I'm going to start very shortly. If I don't use this one, I'm going to probably go with the smaller Neo brother of this one here. First, let's look at how this thing comes boxed, how sexy it is, and then get to the performance metrics. Okay, so I bought these drivers a little while ago, and so I've lost one of the spacer pins there and one of the bags that the driver comes in. So it's not exactly how you get them brand new, but it gives you a bit of an idea of how they're packaged by Tymphany. These are really hefty, well-built drivers. You can tell they're high quality, good thick flange on them. Everything's glued together well and bolted together nicely. Although I gotta say, some people probably don't like the design of this dome. It looks like a nipple. I had to come up with a test piece of wood for the test baffle. I wanted it to be roughly 8 inches, and I wasn't acting here. I found it just like that. It was perfect, so I didn't even have to run it over my table saw. Although I did cut it a bit shorter with the bandsaw. Perfect! I used a CNC to just get the measurements off the spec sheet and pop in a hole to flush mount this driver. Okay, with tweeters, they're really susceptible to diffraction, more so than woofers. It's important that if you use my files and you use this data, that you get the baffle dimensions the same. Same with the woofers and mids, but more so with tweeters. So we're just going to look at those dimensions right now. We have 14 inches, 355 millimeters in this direction. In this direction we have 8 inches, or 202 millimeters roughly. Okay, the tweeter is centered, and it is, the top of the frame is just under 1.5 inches, 35 millimeters. Okay, so that's all important information if you use this data to reproduce the baffle. Now, the reason why I picked the baffle dimensions like this is I figure if you're using this caliber of tweeter, you may use a 5-inch or 4-inch mid, but very likely people are going to put this in a two-way with a 6-inch woofer like that, in a bookshelf, possibly a tower, and if you were to use a tower and extend this baffle, that would be alright too. The more important dimensions are this width, and this 35 millimeters up here is quite important as well. And also, to minimize diffraction, what I'm going to do is I'm going to assume most people would put a chamfer or round over on this, but maybe not all, so I'm going to put a light one. I'm just going to take my hand plane actually and do it. MDF and hand planes don't get along. Realistically, this size of chamfer isn't doing much to minimize diffraction. There, that's pretty reasonable. I think if you didn't use a chamfer and you use straight edges in your designs using this test data, you would still be okay. And if you use a larger round over or chamfer, maybe a full 3/4 inch even, you'd still be okay to use this data. The more important issues are the dimensions that you use a baffle this size or longer. Just test fitting it here. I was going to screw it in, but I found that it snapped into place pretty tightly. I don't even need screws. Okay, here's the first results. This is sample 1, on-axis response. You can see that you get really extended, very flat response. This is excellent. I was really pleased to see this. I've used this tweeter in the past, but it's still, I had forgotten just how good it was. I've been working with compression drivers for a long time now, and seeing this dome was really impressive. This is the beauty of dome tweeters. You usually get a very flat, extended response, but this one in particular, you can just see how incredible the response is. And it goes quite deep too. You see response well below 1000 hertz, though I wouldn't use it that low. And just a little bit of a bump at 1500 and a dip at about 3,000 hertz. Which we can see in the off-axis response is diffraction. So let's do that. So I took measurements, I had the on-axis response, and then 15, 30, and 45 degrees off-axis. And you can see that you get a little bit of bunching, gathering, and crossing of the lines at around between 2000 and well, all the way up to about 4000 hertz. And this is a sign of diffraction. So anyways, beyond the diffraction effects, you can see that we're getting a really good off-axis pattern. Above 6000 hertz, the lines start to separate a little bit, and we get quite an interesting null that we see in the spec sheet as well at around 16,000 hertz. Overall, this off-axis pattern is pretty good. And if you do some things to the baffle to address diffraction, you would probably get an even better pattern off axis. And just to show you how good the response is when you move a little bit off axis, this is the 15-degree sample. So the diffraction is kind of being mitigated a little bit because you're slightly off axis, and you can see just how straight and smooth that response is. And you know, commonly people do sit a little bit off axis, whether the speakers aren't towed in, maybe they're pointing straight out, or they're just a little bit off axis by nature. Okay, then I'm just going to set up for sample 2. I had a line on the ground, that's what I was looking at, trying to get everything back into position. That line on the ground was to tell me exactly where the previous setup was. But despite that, I still use a tape measure to make sure I'm exactly a meter, or actually I was using half a meter in this case. I'm dealing with a little tweeter here, I can get away with that. And there we go. Again, we're seeing very similar response. This is sample 2 on axis, and these lines are almost totally overlaying. If you go back and look at what we had for sample 1, we're getting great consistency here. The sensitivity is about the same for each driver, hardly any variation between the two. We get the same diffraction effects, peaks and dips happening at 1500 and 3000 hertz. Another thing I didn't mention about sample 1 is the sensitivity is pretty good. We're up over 90 dB. This is a 4 ohm driver, so I mean we can sort of expect that out of a 1-inch dome, but pretty good. Okay, and then I took the off-axis responses, the same as before, and again we can see those diffraction effects showing up, especially between 2 and 4000 hertz, and we get the separation happening above 6000 hertz as well. Good consistency here, and ultimately good results. And just for comparison purposes, this is the spec sheet graph that you can get from Tymphany. So we can see that we're getting similar results. They are on an infinite baffle, an IEC baffle, so they're not getting the diffraction that I am, which is a really good way to measure drivers. It's you know, universal that way. But I use baffles because I'm trying to give you real world examples. The downside is you have to use the same baffle as I do, but the data might be a little bit more usable for you. I then went ahead and set up my woofer tester to get the impedance data. Setting up sample 1 here. And we can see that this is roughly a 4 ohm driver as we expected based on the specs. And through the passband, you know, above 2000 hertz, we're getting fairly flat, smooth impedance profile, and below 2000 hertz we see the impedance pick up and eventually reach the resonance frequency, which is extremely low for a 1-inch tweeter. So this is a good thing. It has to do with the large chamber that this tweeter is afforded, as well as just good design by Tymphany here. This is one of the things that makes the tweeter great. You can see a little bit of variation between the two at FS. You know, the 1 ohm difference between the two peaks, it's worth mentioning, but ultimately that's way into the stop band of the crossover, and unless you're dealing with first order crossovers, and even then it's really not going to impact your design. If you are using a first order crossover, you will have to deal with this impedance peak. I think you could work around this quite easily. The most important part is in the pass band, and right where the crossover is going to have most of the action, around 2000 hertz. We've got great consistency, so this is good to see. Alright, there you have it. That's the Vifa XT25BG60-04. It's amazing, and I think I'm going to go for it and use this in an upcoming design. I'm still wondering if I should go with the littler Neo version. I think that's XT25SC30 maybe. Let me know what you think, if I should go with the smaller Neo version or this big chambered, big magnet, power version. If you want to use this driver in one of your own projects, I have uploaded the files for use in XSim or another crossover simulator to my Dropbox account, which I'll link to in the description. If you enjoyed this video and want to check out some of my other driver test videos, you can see a couple here. You can also subscribe to my channel right here, and I'd really appreciate it if you do that, or like the video, comment below, and give me some feedback. Thank you very much. Bye.